Hello, Assalamualaikum warahmatullahi wabarakatuh. We are from Group 7 ECC 3120 and we would like to present a low pass filter for both active and passive filter. So our group member are Aishah, Abdul Hadi, Muhammad Aiman Safwan and Nick Muhammad Farhan. For active filter, we are choosing our active low pass filter. The principle of operation and frequency response of active low pass filter is exactly same as passive filter. However, the difference of these two filters is active low pass filter use an op-amp for application and gain control. The simplest form of a low pass filter is to connect an inverting or non-inverting amplifier, which is the same as an op-amp. Based on the simulation on multi-sim, we are using both probe tool to draw the frequency response. We gain the cut-off frequency is equal to 1 over 2 times with pi RC. Based on the simulation, the cutoff frequency at negative 3.078 dB is equal to 161.626 Hz. And for based on manual calculation, F equal to 1 over 2 times with 3.142 times with 1K times with 1 times 10 power of negative 6 is equal to 159.134 Hz. So that is slightly different from the simulation on the multisim. On the right side, there are a graph of the board plot that we gain from the simulation in the multi-sims.
Hello, I'm Farhan and I'm responsible for the transfer function and the simulation for the transfer function. So this is how we got the transfer function for the active low pass filter. So based on the figure above, this is the figure. The transfer function of the standard simplified inverting amplifier is negative ZF over ZI. So where ZI equal to RI, R1, you will just replace it, and the ZF you need to derive it by this way as 2. So we will get the R2 over 1 plus C multiplied by R2. So after all the derivation, you just need to replace the formula, the derivation you got into the main formula. So we got the negative R2 over R1 multiplied by the R2 multiplied by capacitor plus 1.
Okay, moving on the simulation part of transfer function. The simulation will be done in the MATLAB, and this is the coding. So we will check whether the transformation is right or not. So this is the magnetic response. Okay, this is the noise signal just now that you hear. This is this here, and this is the after the wave filter. So here is the transfer function graph. You can check it whether it's right. And you can move it here, and here you can see the frequency is at 1000.
So you already see the video. You got the frequency of is 1000. So you can prove the generated graph that, whether it's right or not by using the formula 2 pi f. You just replace the value of f with the cutoff frequency, so we get the answer. So we prove that the graph that we use or we get correct. So that's all from me. Thank you.
Assalamualaikum and hi, I'm Aishah and I will explain the passive filter theory and transfer function. So we are studying the passive low-pass filter. The filtering system can be easily created by connecting together in a series single resistor with a single capacitor. The input signal is applied to the series combination, but the output signal is only taken across the capacitor. It is also called the first-order filter, in which it has only one reactive component, that is the capacitor. For the transfer function equation, in S domain is 1 over 1 plus SCR. If S equals to J omega, the transfer function will be 1 over 1 plus J omega CR. And to relate with frequency response, it will be 1 over Z1 plus omega CR squared. Thus, from this equation, we simulated the transfer function on MATLAB. So from the derivation, we got HS equals 1000 over 1000 plus S. Okay, so this is the circuit involved for the transfer function. We have sine wave, we have transfer function, and we have scope. So for the sine wave, we use time base, we use simulation time, we have 1 volt as amplitude, and for the frequency, let's set it to 10 Hz. And for the transfer function, we got it from the equation, the 1000 over S plus 1000. So let's run it. Okay, so for the scope, we got 1 volt peak for the amplitude, and this is the waveform. So let's see if we change the frequency to 200 Hz. Okay, so as you can see, the frequency becomes higher, but the amplitude becomes lesser, up to 0.6. This indicates that the low-pass filter will allow low frequency and block high frequency from passing through the filter. Okay, with that, I will pass this presentation to Hadi. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. I'm Hadi. I will continue my part with the response simulation for passive low-pass filter. Firstly, I will explain how the passive low-pass filter in the multi-sim. For multi-sim, component I use is resistor, capacitor, and AC voltage. The output we use is put plot to see the output and the waveform cut-off frequency in the graph. The output of the board plot is connected across to capacitor to apply the low-pass filter. For low frequency, we can see the gain is almost constant, and as the frequency increasing, the gain is decreasing. When the frequency increases until negative 3 dB, the graph will become steeper. This is because the low-pass filter has filtered the high frequency more than negative 3 dB. The graph will become steeper much more when increasing the number of order filters. Next, we look into response simulation in the MATLAB. In the MATLAB, we have to determine the equation to design RC low-pass filter. The equation we use in the RC low-pass filter is Vin equal minus Vout equal to RC derivative d Vout over dt. We use RC low-pass filter equation has because contain two components, which resistor and capacitor only. In this MATLAB, we have to place the main signal and noise, then adding block to add these sine waves. The scope for the output is used to output waveform. As you can see, the original signal that contained with noise have been reduced in the RC low-pass filter. The graph in the RC low-pass filter shows the original signal has filtered amount of the noise. The graph will be more smoother when the gain is increasing in the RC low-pass filter. That's all from me. Thank you.